So welcome back, everybody. And today's topic is logistic regression. And that, as I said, is going to serve as a stepping stone towards gradient methods and the optimization problem per se. And if we now switch into the whiteboard, I just wanted to bring up some of the things which we have done and try to link this with what is going to come now. So if we look back at what we've been having, so we've been trying to fit a function to the data. So we have our data. Let me just wipe this out. Y of I, which we now assumed could be described by some function which depends on our input plus epsilon of I here. And I'm going to do one small thing here so we are not getting disturbed by emails. So you don't hear the ping every time I... So one of the things which we made as an assumption here is that this function is a deterministic function and that there exists a continuous function. And the other assumption we made is that these epsilon of i's, they are given by a normal distribution with zero mean value and a variance sigma squared. This is the basic assumption which we made in the fitting of the data, assuming that our data can be represented by a continuous function. Now, suppose now that we are looking at data which are given by discrete classes. So suppose now that we have a data set which looks like this. So we have some x1 and some x2 here, and x1 could be hours slept, and x2 could be hours we've been studying. Just to give you an example. And then we could look at a case where we now want to see if there is a correlation between these two quantities and the average grade which we get in a course. So suppose now that we monitor a group of students during a semester, and then we actually ask them how many hours did you sleep a day and how many hours did you spend on this specific course. And suppose now that the circles represent a grade which is above the average, and the crosses represents now a grade which is below the average. Now, what we want in this case is to actually define, based on hours slept and hours studied, whether we can split the two classes. Now we have a discrete output. So we could now say grade above average. And here we could have a grade below average. Now, you could obviously fit a line here, right? So if we want to, we could say that, okay, let's insist on our linear regression. And we could say that now, okay, let me fit this so that in case I now have this line here, so this would follow from standard linear regression. We could take even the ordinary least squares, standard OLS. And then we would say that if now the result is above the line, so suppose now all the points on the line give you y equal to 0, and then you would say that everything above the line is a +1, which corresponds to a grade above the average. And then you could say that everything below the line corresponds to -1, which is a grade below average. So what we have then is to have constructed a line which separates the two data sets. So this is fully possible with the kind of machinery which we have developed. So we could have used linear regression, which is tailored to fitting a continuous function, like the one which we put up here, to actually add discrete output. Because what you could say now is that your y's, the y of I, could in this case be equal to +1. And the y of i's here could be equal to -1. So it means that you have in the input to your machinery, you have said that if I have y of I equal to 1, then it's a grade which is above the average. And if I have y of I minus 1, it's a grade below the average. So this is fully possible to actually do with what we have done. Now, it would still be a classification problem because we are not fitting a continuous function f of x, but we are fitting discrete outcomes. So this could be the type true, false. It could be 0, 1, depending on what you have, yes, no, etc., etc. Now, you can increase the number of so-called classes or discrete outputs. So you could look at whether a patient coming into an emergency room has had a stroke, a heart attack, or is just suffering from flu, etc., etc. So these would also be different types of classes. And the problem, you can obviously make the problem more and more complex if you want to. So this is a situation where we can find and fit a straight line which separates the two classes. However, suppose now we look at another data set. Suppose that we are looking at the credit card debt and whether people will pay their credit card debt or not. So this is a typical case. I mean, it's one of the famous data sets which many people have been using in training different machine learning methods. There is a famous data set from Taiwan with 30,000 entries where you have something like, I think it's 15, 20 features, which goes like the age of the person, occupation, level of education, whether you're single or not, etc., etc., and whether you will pay your credit card debt or not. So this is whether you default or not. So that means that in this case, you could say that 0 here would be you defaulting on your credit card debt, and 1, sorry, not defaulting, but paying your credit card debt, and 1, you not paying your credit card debt. So you have now labeled your data with 1s and 0s. So these are the outputs, the y's. And the depth here is actually your x's. So you could now think that you have observations of this type here, and there may be some observations here, but then suddenly there's a jump here. And then you have all the people who don't pay their credit card debt, like this. Now, I could still fit a straight line here if I wanted to, but you would see that this is not really optimal, right? And there are many problems as well. So you could fit a line, could go like this. Now, the problem in this case is that this line fits actually a function where y of I goes from minus infinity to plus infinity. What we want, however, is that y of I is now either 1 or 0. So this is actually what we would like to have. And one thing we could do now, instead of fitting a straight line, we could try to fit a more complex function. But what could be done now is to replace this straight line with something which looks more like this. So you could now think of something which we fit, which looks more like this S-shaped function. Then what we would say is that if the value is less than 0.5, then the output is 0. That means we pay our credit card debt. And if the output is larger than 0.5, we do not pay our credit card debt. So you could now say, if you look at this, suppose this is 0.5, then you could say that if less than 0.5, that means that your model, and now I put a tilde here, y of I is equal to 0. And if larger or equal than 0.5, then y of I tilde, the prediction which we make, is equal to 1. So what we are going to do now is to replace this function f of x with a probability. Now, this function which you see here, this plot here, is something you can mimic with a very popular function, which is called the sigmoid function. And you're probably seen this many, many times, or the Logit function, just a Logit from logistic regression. So a very popular way to define this is, and this is something which we're going to see now pretty soon. So what we have done, what we are going to do now, is to replace this function f of x of I with a probability p of x of I, where this p of x of I is now a function which takes values in a domain from 0 to 1. So we have assumed that it has been normalized, and it's going to play the role of a probability. So we would then say, if we can fit such a function, we are now going to say that this is a function which, if it's smaller than 0.5, then we make a prediction 0, or -1, or true, false, whatever we are looking at as a classification output. And then if it's larger, we would say that it's equal to +1. So what we have done is actually to now going to try to replace this with a probability distribution. So what we are saying is that there is a probability of finding our y's, which is given by this function p of x. And one of the simplest ones, so a simple variant, p of x, and now I'm just going to put an x here instead of y, x of I, is actually to write this in terms of e to the power of some argument x divided by 1 plus e to the power of x. But normally what we end up with is something like this. So we would have e, this is the simplest possible form, a beta 0 plus a beta 1 times x divided by 1 plus e of beta 0 plus beta 1 times x. So I shouldn't put an equality sign here. So this is the one which we are going to look at. And this function here has two unknown parameters, beta 0 and beta 1, which we need to determine. We could now say, in principle, we could say that our x goes from -infinity to +infinity. And in principle, x could now be defined from -infinity to +infinity. But in most cases, x will be defined within a specific domain. Now, this function here is normally the function which we call the sigmoid, or the logistic function, or it has many, many different types of names here, but the sigmoid function is the most common one. Now, one thing you will also see is that this function is normalized. If you take the log, so we have two outcomes. So if p of x is less than 0.5, then y is equal to 0, or it could be -1. But now we're going to specialize to putting y equal to 0. So you can always make a mapping. So you go from 0 and 1 to -1 and +1. So this is up to you and how the data have been labeled in your input files. And then you would typically then have p of x larger than 0.5. Then what we would have is that y is equal to 1. So this is a pretty common case. And what you see now is that the probabilities, if I now define, so what I'm going to do now is to introduce a kind of shorthand. So I'm going to use a notation now where p of x is given by this function e to the beta 0 plus beta 1 times x of 1 plus e to beta 0 plus beta 1 of x. And this is the one which I'm going to have. So when now I'm looking at specific values, I'm going to have beta of I as an output of x of I, and these parameters beta. This is given by p of y of I equal to +1 of x of I of beta. So that means what is the probability of finding y of I equal to 1 given, which is the bar, x of I and beta. This is the way we read that specific formula which you have here. Then, since we have only two outputs, so this is a discrete set of events, that means that if I now want to define P of y equal to 0 with a given x of y of beta, and by the way, I'm going to label this as just P of I. It's just going to be a shorthand in the calculations here. This is obviously given by 1 minus this P of I. Because that's I have only two possible events, either 0 and 1. And if you now look at the probabilities, if you now sum this, take the sum of I from 1 or 0 up to I equal to 1, in this case, the number of events which we have, and then I take P of y of I, and then x of I of beta. This is, if you sum it up now, you see that this sums to 1. Okay? So these are just definitions which we're making. And you can now take the ratio. There's another interesting function now, and this is called the Logit or the Logit Transformation. And that's normally a g of x, which is given by the log of this function, p of x. So p of I. So we have an I here, and 1 minus p of I. And if you do the math then, take the ratio between these two probabilities, what you get then is beta 0 plus beta 1 multiplied with an x of I. So there you are back to the kind of linear representation which we had in linear regression. Now, there's nothing which limits you if you go back to the assumption we made. So what you see here is just a plain assumption which we have made. There's nothing which hinders you to have a more complex function of beta as an argument in the exponentials. So you could have a kernel which relates transformations of the x's. You could have polynomials which represent the x's, and so on and so on. That means more complicated functions. And you could have more than just two features. So you could have, if you're looking at this credit card data, we are now just limiting ourselves to two parameters, beta 0 and beta 1. But you could think of you, if you're looking at the credit card data, you have something like 15 features. Or if you look at this famous Wisconsin cancer data, that has something like 30 features, like the thickness of the tumor, the color of the tumor, the size of the tumor, the radius of the tumor, etc., etc. So these will all be features. So that in that specific case, we would have something like a beta 1, beta 2, beta 3, etc., etc. And you can make this more complex. So this, what you see now is something which I have set up as the most simple probability which we can define in terms of only two parameters. That means that we have only two features here. But there's nothing which hinders you from having more complicated functionalities here. Any questions so far? Is this something, how many of you have seen this before? Okay, 1, 2, 3 of you. So what I wanted to have you with me is this transformation which we make now from a continuous function, which in sometimes could be used for classification problems. If we can have such a simple domain here, where we can split everything, the two outputs. But in other cases, this is not very easy and straightforward. And then it's much easier to actually replace that continuous function with a probability. So in the standard approach which we used, we ended up with a value. So if we now go back to linear regression, so let's just look at the connections here. So in linear regression, we had a function f, which we wanted to fit. So we ended up with y, the output, which is now approximated with this design matrix multiplied with beta, plus this normally distributed noise. And this is something which we rewrote in terms of our model plus an epsilon. And then we use mean square error as one way to gauge the quality of the model. And then we wanted to optimize the mean squared error. Now, one of the things which we found when we did the statistical analysis is that these y's are actually given. So y follows a normal distribution with a mean value x times beta and a square variance, which was given by the variance of the normal distributed noise epsilon. So this is a distribution which then governs our results y, or the output which we are trying to fit here. And as you may remember from last time when we met, we actually derived ordinary least squares using a statistical assumption where we took every y of i's to be independent and identically distributed, given by a normal distribution. And then if we optimized this probability distribution, we could then find the same equations for the unknown parameters beta as we did when we just set up a plain linear algebra approach. So that gave us a statistical link with the output, assuming that the function which we have is a plain deterministic one, and that the stochasticity or randomness comes from the noise which is added to the data. So these are important assumptions which we have made. So even if we make a model here, we have actually made an overarching model in the sense that we assume that our data have a noise which is normally distributed and that they are described by a deterministic function f of x, which is continuous. Okay. Now we are going to make an assumption. In this specific case, we are now going to make an assumption that y is now given by a probability p of x, which we don't know, plus some noise again, but we don't know the noise. So then we could ask the question, I mean, what kind of distribution is this noise following? And what kind of distribution is this y following? Based on these assumptions which we have made. So let's try to see if we can find out what kind of distribution y is following. So which distribution does y follow? Yeah.
This new case is independent of this new assumption, this new approach.
Yeah.
It's independent of the.
Yeah. So because now we are actually dealing with a classification problem. So what we want now is not to have a continuous function, because if you look at the case which you have here, a continuous function would make predictions from minus infinity to plus infinity. But now we simply want to reproduce discrete outputs. So we are now simply replacing. So I should have written that now, replace with. And then we can also ask ourselves which distribution does epsilon follow? Now, what we're going to do now is actually to make a model. So what we said is that when y of I is equal to 1, then the probability, let's just make this a little bit simpler, p of x is equal to p. So I'm just trying to not carry with me too many variables, if that's okay, okay? And we know that in this specific case, it could be, this is just an example. It could be this beta 0 plus beta 1 divided by 1 of e to the beta 0 plus beta 1 times x. So here we're just assuming that there is a probability p, period. And then what we have is that y equal to 0. That has probability, this is a good spell check here. probability 1 minus P. Because there are only two events here. Now, if y is equal to 0, then what we get, that has epsilon equal to y minus P. Because I have assumed now that y is equal to P of x plus epsilon. So epsilon then, if I put y equal to 0, then epsilon has simply to be equal to 1 minus P, right? And if I now take, if y is equal to, no, sorry, if y is equal to 1, sorry for that. And if y is equal to 0, then what we have then is that epsilon is equal to minus P. With probability, so with probability, one minus P. And in this case, when I have this specific case here, then I have probability with probability of epsilon, or actually probability just equal to P. So let's just frame that one in here. And then we have the next one here. So that means that we now assume that this quantity epsilon has a mean value equal to 0. So that means that when we set it up now, what we have is that epsilon, the mean value of epsilon, would then be equal when I'm now putting up the probabilities. So I have epsilon for the one case is 1 minus P, which is what I had up here. And it has a probability equal to P. So when I'm setting up the mean value, so let me just quickly put up this. So this is P, and then 1 minus P here. So if you now look at an expectation value of any quantity x, that is given by the sum, if we know the probability of P of x of y, multiplied with x of y, and then we sum over the domain of events. So I have two events here, 0 and 1. So what I'm simply doing now is to calculate the mean value. And when you now look at what we have here, we actually get that this one is equal to 0. So this is an assumption which we can make. Then I can calculate the variance of epsilon. So with the mean value is actually equal to 0. And if I calculate the variance, what I'm going to get then is now the value itself, 1 minus P squared, multiplied with P, the probability. And then plus, and then I have minus P squared, multiplied with 1 minus P, which is a probability. And if I now add these together, what I get is P of 1 minus P. So let me now ask you, does any one of you remember what kind of distribution has this kind of variance?
Binomial.
The binomial. So what we have, and this is in the way expected, because we have two events, right? So in a certain sense, what we are just confirming now is what we started with. We have two events. So the binomial distribution is a pretty obvious candidate. So that means that epsilon follows a binomial distribution. A binomial distribution. Now, the question which we're asking ourselves now is, how do we model our system? And how do we find these parameters beta? So what we're going to use now is to define this maximum likelihood, which we defined when we derived ordinary least squares using the normal distribution and assuming that all the events are identical and independent, identically distributed and independent. So we're going to make an assumption now. And this is a pretty standard assumption. Y of i's are ID. So that means that they are independent. So the first one is independent. And these two words stand for and identically distributed. And what we've said now is that Y of I is given now by this probability. So Y of I equal to 1 has probability P of X of I, which we also wrote as a P of I. And this is the same as P of Y equal to 1, given an X of I and this unknown parameter beta. So this is where we are going to put our modeling into this probability P. So we don't know this probability P, and we are going to pick a model for it. So you can actually change these probabilities according to the type of system which you have, depending on the data which you have. So you can actually have different assumptions for this probability P. So you can think of the way we did in linear regression, where f of x was replaced by a model which we made. It could be a polynomial fit, it could be a more complex function than just a plain polynomial, and so on and so on. And then we're also going to have y of I equal to 0. That has probability, which is just this 1 minus p of x. Has probability, which is 1 minus p of x of I, which we also wrote as a p of I here. So that means that since we now have a binomial distribution, we now make the following ansatz for the probability of p of y. So that means that what we're going to assume now, we assume a binomial distribution. And we are going to make a model for y, which is going to be given by this p of x of I to the power of y of I. And remember now that y takes only values of 0 and 1. And then I have 1 minus p of x of I to the power of 1 minus y of I. And then you see that if y is equal to 1, then the second term is just 1, and we get the probability which we're looking after. And if y is equal to 0, the first term is 1, and then the second term is simply the 1 minus px of I. Okay? Does that sound plausible? So this is now the way we are going to model. And then we have the domain D, which now consists of all our data. So we have x0, y0, x1, y1, etc., up to some x n minus 1 and y of n minus 1. And remember now that the x's, they can actually be an object which represents different features. So I'm not specifying here whether this is a matrix or vector, the x's. So I'm just leaving it as it stands. X are the inputs and y's are the outputs. Now the y's, as we have decided already, y of I, are simply given by the 0 or 1, or true, false, minus 1, plus 1, or whatever. Then the probability of finding the output y with a given input and given this parameter beta, as we did before when we set up the ordinary least squares equation based on a Gaussian distribution. This is now going to be given by the product of all these probabilities of n minus 1, and then I'm going to have the p of I to the power of y of I, and 1 minus p of I to 1 to the power of 1 minus y of I. So this is my model for the probability. Okay? And now I want to find the betas which maximize this probability. So beta hat now, the optimal ones. Optimal beta, which we write as a beta hat, is now given by max, or the max argument of beta, which now lives in this parameter space or feature space of length p, of this probability p of d of beta. Okay? Yeah.
The multiplicator.
Yeah.
You only can do that because you're assuming IID, right?
Yeah, exactly. So this is a basic thing which we do, and which you can actually criticize many of the models which we are setting up. So we did the same when we derived ordinary least squares. We simply assumed that the y's follow the normal distribution, and then that they were independent and identically distributed. So you could say that this is us setting up a model based on our lack of knowledge. So I want you to keep this in mind all the time, because there are many basic assumptions. So you have the kind of feeling that everything is black magic and fantastic, but these are assumptions which we make about the inputs to the theory. And we know that there are many, many cases where the events are not independent and where they are not identically distributed either. Okay, so then the thing we can do now is simply to maximize or minimize. However, when we want to maximize a product, this is something which is a little bit more tricky or not that straightforward. And the equivalent problem, as we discussed earlier when we did ordinary least squares, is to take the log, right? So what we can do then, we can then look at the equivalent problem, but we could also look at the equivalent problem where we minimize. And minimization is the kind of standard convention which we do. So you can maximize or minimize, but the standard convention is actually to minimize. And this has to do with the fact that many functions, a good set of functions do actually have lead to minimization problems. We're often looking at the minimum of the energy or the minimum of something. So if you just put a minus sign, then you go from a maximization problem to a minimization problem. So what we can do then is actually to minimize, and the equivalent problem then is actually the log, minimizing the log minus log of this function p of d of beta. And whether you minimize log 2 or log 10, the base you have, that is just a scaling factor, right? If you take the base of log 2 or the log 10 of a given parameter, it just scales the value. So it's up to you to decide which function you find the most convenient one. In this particular case, it could be log 2 because you have only 2 events. But that's a matter of taste. So if we do that, what we need to optimize, and now it's time to take a small break. So what we need then is to define this cost function. And this has a name in the literature, is actually called the cross entropy. So we could now do log of p of d beta. And in our case, this is now simply minus. And now it's time to take a small break. Equal to minus. And then we sum over all the data which we have. And then we get a y of I of ln or log of p of I. And plus 1 minus y of I of log of 1 minus p of I. So this is the case when you have a y being given by 0 and 1, but you can map this, the change of variables from 0 and 1 to minus 1 and 1. That will only change the exponents in your probability distribution. So you can easily make that mapping to another type of output. But now we just decided to have 0 and 1. And then the next thing we need to do now is simply to calculate the derivatives of dc of beta with d beta, and we want that one to be 0. So that's for our topic after the break. So I see that everybody's eager to see the continuation of this. So this is like a TV series which goes on and on all the time. But now it's time to take a small break, right? Let's do that. Okay, welcome back again. And what we're going to do now is to go through the mathematics here, just calculate the derivatives. And we are going then to look at the kind of equations we need to solve. And now what you will see rather quickly is that in this case, we don't get a nice analytical equation for these parameters betas. You remember from linear regression, when we took the derivatives, and in linear regression, what we had was a linear dependence on beta, right? As you have here. And that also gave us a very simple equation. But now we don't have a linear dependence on beta due to the exponential. And it shouldn't be a surprise then that we won't get a nice analytical solution for the parameters beta. And we would have to find these parameters numerically. And this is simply just follows from the ansatz which we have made. Okay? And that ansatz is the more general case because normally we don't have this nice linear behavior. In most cases, we have some more complex dependency on the unknown parameters. So the linear regression case, which sounded like a very nice cushion where we could do all things analytically, this is normally not the case in basically all applications in machine learning. And what we end up with then is to have to take the derivatives here. And I hope you don't get offended, but if I now take the log of this function, log of p of I, this function, if we now just do the math here, this should actually be equal to beta plus beta of 1, the parameter x of I. And then we are going to have minus log of 1 plus e to beta 0 plus beta 1, the parameters. And just keep in mind that we are not limited to have only 2 parameters. We could have many parameters reflecting different features in the model, which we have. So when we do that and we plug this into the function, what we are going to get is that this function c of beta is now, in our case, going to be equal to a sum of all the data which we have. And we are going to have y of I. And this is multiplied with beta 0 plus beta 1 times x of I. And then I have minus of 1. So I have the variable 1 minus, there should be a 1 minus y of I. 1 minus, no, right, wait, this disappears. So if I've done things correctly, it should be minus log of 1 plus e to the beta 0 plus beta 1 of x of I. And then we take the derivatives. And when you take the derivatives, then we can now take the derivatives with respect to these 2 parameters. So we have a beta 0, and we want that one to be 0. And if you do the math, then you will see that this becomes equal to minus I equals 0, n minus 1. And it's pretty easy to see that this is going to be given by y of I. That's the first term. And when we take the derivative of the log, this is going to give us back the probability itself. So we're going to get a p of I in here. And this would now be the first gradient. So we could call this for a G0, G for gradient, okay? And then we have the next one, which is D of C of beta 1. We want that one to be 0. And if you take the derivatives, then we get, an x of I. It's not so difficult to actually do this, so I'm not going through the derivation, because then I guess you guys would be offended if I went through derivatives of logs and so on. So I'm just stating the results. In general, what we would see then, in general, when we look at the general equation here, we have, and now we are looking at the vectors. So when I skip the specific subscript 0 and 1, now this beta is now a vector. In this case, it has length 2, but we want that one to be 0. So you will find that this can be rewritten as X transpose, the design matrix, multiplied with Y, the output, which are either zeros or ones, and the probability P. So P is now a vector with all the probabilities. So P and Y, they are now vectors of length n, the number of points we have. And you remember also that X is our design matrix, and that is a matrix of dimensionality n, the entries, times P, the number of features. In this specific case, P is equal to 2. So I have beta 0 and beta 1. Now, one thing, and I leave that as an exercise, and that is to show that the second derivative of C with D of beta of T of D beta is actually given by this design matrix transposed times a matrix W times X, and this is called the Hessian matrix. And this W is a diagonal matrix, diagonal only, where the values Wi are given by P of I multiplied with 1 minus P of I. So that matrix contains now only diagonal elements. And in this specific case, what you will see now, since the probabilities are always larger than 1, or no, larger than 0, it means that when we look at the matrix X transpose times X, times something which is always larger or equal than 0, this matrix is going to be semi-positive definite, which means that we are going to have, again, a convex optimization problem. So the second derivative will always be larger or equal than 0. And that's very important, because that means that we are actually searching for a minima, and we are going to obtain a minima, since the matrix is semi-positive definite. One can actually show that. So if you go back to linear regression, just a quick reminder. Then in linear regression, what we had for ordinary least squares, then we had the second derivative. Actually, it should be d beta t. It's not, sorry, because this is a matrix. And this is was equal to X transpose times X multiplied with 2 divided by n. So we derived that one a little bit earlier. And that leads to a matrix which is positive definite in our case. Now, in linear regression, what we also had was that the parameters beta, the optimal ones, were given by, and this is just ordinary least squares, the inverse of this matrix times X transpose times Y. So this is gives us a nice analytical expression as long as we can calculate the inverse of the matrix. In this case, however, what we have is that dc d beta, which we can write as the gradient g of the cost function, is now given by either minus, or we can rewrite it as X transpose of P minus Y. And we want that one to be 0. Now, if you look at the expression which you have, this is something which is not linear in the unknown parameter beta, because beta enters as an argument to P. So if we now look at the model which we made, so our model here, says that this P of I is e to the beta 0 plus beta 1 times x of I divided by 1. So this is just one possible model which you can make of x of I here. And in this specific case, what we see now due to this nonlinearity, so due to the nonlinearity, since we have a exponential dependence of beta, we don't get a nice analytical expression. A simple analytical expression for beta. So we have a nonlinear model in the unknown parameters beta. So if you now look at the problem which we have here, so we actually want this DC d beta, which is given by the design matrix transposed times the probabilities minus the output equal to 0. This is the same as us trying to find the zero of a function, finding the root of a function. And now, if you now spool back in time and look back at some famous numerical algorithms, which famous numerical algorithm is the one which comes to your mind in finding the roots of a function? That's, yeah, but that is named after actually, since I'm a physicist, I have to say there's a famous physicist which actually developed the method. It's Newton's method, or more correctly, Newton-Raphson. So Raphson was Newton's assistant who actually derived many of these mathematical algorithms. So the simplest way you typically do this is by Newton-Raphson's method. So that means that, and what I want to do now is to give you the overarching picture of it. And then we are going back and we are seeing how we can understand what we are solving and why we have methods like gradient descent, steepest descent, conjugate gradient descent, which are some of the standard methods which are used to find the roots of such a problem. But the basic way, so let me stay at this kind of overarching level. So the basic recipe, or what we might say is a standard recipe, you have all these kind of second methods, the simpler methods, but the one which people normally start with is the Newton-Raphson method, which is actually you making a Taylor expansion of the cost function to the second derivative and leaving out everything else. So you will see that in just a few moments now, that what we are going to do now is to take this cost function and make a Taylor expansion, and then just stop at the level of the second derivative. So that's essentially what we are going to do now. And that gives us Newton-Raphson's method. So the basic method, that's Newton-Raphson, or just Newton's method. Sometimes it's intimidating to see how these famous scientists pervade the scientific literature. If you go and see the name of Gauss, it just pops up everywhere. Sometimes it can be a little bit intimidating because you ask yourself, is there any place for me? Okay. So if you look at the basic Newton-Raphson method, that means that what we are ending up with is to solve iteratively. So this is an iterative solution. Where we now have, after iteration, k plus 1. This is now given by the previous result of beta of k, iteration k. And this now contains now the second derivative, because if you think of Newton-Raphson's equation, you have a function which you want to find the roots of, and that will depend on the function value in the previous case divided by its derivative. But now we want the roots of the gradient. So that means that we need the second derivative of the cost function. So we are going then to have H, which is the second derivative, the Hessian matrix. And we need the inverse of that one. So I'm going to write this as -1. No, not like this, but the inverse -1. And this is calculated at beta at the value of k. And then it's multiplied with a gradient with input beta of k, the previous value. So this is what we need to solve. Now, this is going to lead to a lot of headache and pain. So this is the true bottleneck of all machine learning algorithms. So the simplest way, or you see now immediately also what is one of the main problems. One of the main problems is this one. So we have to invert a matrix, and we have to calculate the second derivative. So if you look at this matrix H, so this matrix H is actually going to be the second derivative. So it's going to have this second derivative, d beta 0, d beta 0. It's going to have dc, d beta 0, d beta 1, and all the way up to to the features which we have of beta 0, of d of beta p -1. And then I will have along here, I will have a similar dc and d of beta of p -1 of d beta 0. And this goes all the way up here. So this matrix has a name. Does anyone remember the name of that matrix? It's named after another famous mathematician and partly physicist. It's called a Jacobian. So we have to, you see, one thing, you need to calculate these derivatives. And if you have many features, this is something you would like to avoid. Then, even if you can calculate this, so if you're doing cancer research and you want to retrace which part of the DNA is responsible for a specific type of cancer, you may have hundreds of thousands of features. So it means that this matrix could be a matrix which has dimensionality more than 100,000 times 100,000. And if I'm using this recipe, it means I would have to calculate these derivatives at every iteration. So you see the complexity here, right? So this is something we want to find ways of evaluating in as quick as possible way. There's more to the picture. When you look at this simple case which we have here with logistic regression, this is not so bad. We have only some few parameters. But if you deal with neural networks, you typically have millions of weights and biases to fit. So that means that your matrix is going to be a matrix with huge dimensionalities. And you don't want to calculate second derivatives of the cost function because that takes a lot of time. Even the gradient takes a lot of time. So you would like to approximate this one with something. So what I'm going to give you now is more the kind of overarching view of all the evilness, all the evil stuff which is going to come, right? And the approximations which we need to do. The other thing, even if you can calculate all these second derivatives, you need to invert the matrix. So matrix, if this is a matrix of 1,000 times 1,000, and you do, let's say, 1,000 iterations, so suppose K is 1,000, so you're then calculating these derivatives, 1,000 times 1,000, that's the size of the matrix. You're going to invert 1,000 times 1,000 matrix 1,000 times because you do 1,000 iterations. Now, to invert such a matrix goes like 1,000 cubed floating point operations. So this is definitely not something you want to do too many times. So what happens then is that basically in all of machine learning, in all, essentially I'm going to put all here, in all algorithms, whether these are support vector machines or you're dealing with neural networks, deep learning methods like convolution neural networks, recurrent neural networks, etc., etc., etc. What you want to do then is something like this. So you have a k plot 1, you have your previous value, beta of k, minus some gamma of k, and multiplied with a gradient evaluated at beta of k. So this introduces a parameter, and this is the stuff which we are going to discuss now. So I'm often using logistic regression because it's a kind of stepping stone towards the complexity of calculating these gradients and these updated parameters by iteration. So in all algorithms, we end up with something like this, which means again that we have a new parameter, and this is called the learning rate. And that becomes a parameter in machine learning. However, what you see is that you still have to evaluate a gradient. So if you now spool back a little bit, if you look at your gradient here, if you now go back and look at the expression we have for the gradient, we have a matrix of dimensionality n times p, or actually in this case p times n, multiplied with this quantity here, which is a vector. If we are dealing with a standard linear regression, we actually have a second derivative, which involves a matrix calculation, and a gradient, which here, I forgot to put it, because the gradient here contains now the x transpose times y multiplied with x transpose times x and the unknown parameter, which means that when we calculate the gradient, if you look at this expression here, we have a matrix multiplied with a vector. So if you have 100,000 data points and 1,000 features, then your matrix is of a dimensionality 100,000 times 1,000. And this is transposed, and then you multiply with a vector here, which has length 100,000. That gives you roughly, if it's a square matrix, which is simpler, if X is a square matrix, then it's n cubed floating point operations to perform the matrix multiplication. And the more data you have, the more time this is going to take. And if you need many iterations to find the optimal values here, that means that you need to evaluate this gradient many times. But there's more to the picture than meets the eye here. If you look at the gradients, what could happen is that your function you want to optimize, if we now just stay in one dimension, suppose this is a function f of x, your function could look something like this. And ideally, you want to find this point. Now, normally you would start your Newton method or your favorite gradient descent method somewhere with a guess. So that means you could start here. Now, when you then use your gradient optimizer, your gradient descent method, which is one of the standard ones, when you reach this point here, your gradient doesn't change, but then you're stuck in a local minimum. So it means that you need some kind of random way of starting where you place yourself. And that leads to recipes which are called stochastic gradient descent and batch gradient descent. So that means that you would calculate the gradient with different starting points. And then hopefully then if you start here, you will find the global minimum. And then you will also start in many other places, but you would then you will actually end up, if you start randomly and you do many such random searches, you will actually end up in the right local global minimum. There are also other problems, which you see like this one, which is a typical saddle point. So that can also lead to numerical instabilities. So what we are opening up now is something like the hard problems in machine learning. Because whatever we do, we have a cost function with a given number of parameters. That means that what we are going to see is a rugged, highly dimensional surface, which we want to optimize. And finding the optimal parameters is thus a not very trivial exercise. So let me just summarize. So we have one problem is the calculation of the second derivative. And the other one is actually the calculation of the gradient itself. particularly if we have lots of data. So I'm going to put some arrows here. So this is going to lead to, for the gradient, G of beta of K, this is going to lead to different methods, but one of the most popular ones is actually stochastic gradient descent. Or we can also use plain gradient descent. So efficient, if you just keep a main keyword here, efficient evaluations of the gradient. Just keep that as a kind of overarching keyword for what is coming now. So standard gradient descent means that you run through all the data points which you have in calculating the gradients. What is common is something which is called batch stochastic gradient descent, where you actually calculate over all the data points, but you split your calculations in batches of less data points. And that leads to fewer floating point operations in total. And it also allows you to hopefully hit the global minimum instead of just being stuck in a local minimum. So this is one part, and this is going to lead to further varieties, which is called momentum gradient descent. And I actually prefer another word for it, which is called memory gradient descent. And I'm going to use GD for gradient descent. So from now on, when you see SGD, that's stochastic gradient descent. If you see just GD, it's gradient descent. So gradient descent means calculating the gradient with all data points. That's the way you should read it. So these are the two variants. So let's highlight them. And these are things which we are going to look at. So we have that one. So we have momentum gradient descent, but we can also have momentum stochastic gradient descent. Momentum stochastic SGD. This is a way to speed up the iterative process. And what you're doing is just to, let me explain this in words, and then we're going to look at the implementations of it tomorrow and on Wednesday. So with the momentum descent of memory, what you're doing now is that you're keeping track of the value of the gradient in a previous iteration. So if your gradient varies a lot from one step to the next one, it will take a lot of time before you find the minimum. If you keep information on the previous step, what you're doing then, you're smoothing out the gradient with information from the previous step. And that can dampen fluctuations in gradients. And you will see often that this method allows you to arrive at the minimum with less number of steps. And we will see applications of that tomorrow and on Wednesday. So this is a very common technique, even if you don't do anything with this learning rate. But then comes the next step, which is the big step. And that leads to a parameter in our theory, which is called the learning rate, as we said. So let me just put arrows down here and continue all the way down here, because now we need some more space. So this is the learning rate magic. And we have many different approaches to that. So you can simply have a fixed parameter, fixed gamma, okay, equal just a gamma. So what is pretty common is now that you could choose a set of gammas, you could now just fix a set of values, 10 to the minus 5, 10 to the minus 4, up to, let's say, 10 to the minus 1. And then just run your calculations with a fixed learning rate. That's just called often just a plain gradient descent. with no magic behind it. And you're simply, sometimes it's actually cheaper to run the calculations with fixed learning rates and not doing anything than just making an attempt to calculate the learning rate with some information about the gradients. So remember now that this learning rate replaces the inverse Jacobian matrix, which is represents the second derivative. So the second derivative is the animal we don't want to calculate. And by using this kind of learning rate, you can actually tune it and use the value of the learning rate, which gives you the best mean squared error, as an example. So it sounds strange, but sometimes you may actually be able to hit the right learning rate and then just get a very good convergence of your method. So that's the simplest possible way of doing that. But then you have what are normally called schedulers, or schedulers for gamma of k. So what you could have is like your gamma of k, a very typical one is that it goes like an exponential. You have a gamma 0, which you start with, which could come from this list, which you have on the line before. And then you have an exponential decay with some parameter k, which now depends on the number of iterations you've done, and applied to some kind of parameter tau here, which you need to specify. We're coming back to these kind of parameters. So that introduces more parameters. So your learning rate is changing as a function of the number of iterations. You can have a linear dependence and so on and so on. So what you might call these for, these are just called ad hoc schedulers for the learning rate. So it's still you not wanting to deal with any information about second derivatives. Then we have the more advanced ones, which are called the adaptive learning rates. And they keep some information about the gradients. So that means for every iteration, you try to bake in some information about the gradients in the calculation of the learning rate. Adaptive learning rates. And here you will find famous methods like ADAM, the one I mentioned, which has more than 120,000 citations in 8 years. Pretty good. There's something which is called root mean square propagation, or RMS prop. Root means squared propagation. And we are going to look at that on Wednesday, just called RMS prop. This is another popular method. Then there's another one, which is called ADA grad. So this is just adaptive gradient. That's another one. And you have a whole plethora of such methods. And this is actually where when I said half jokingly that if you want to get many more friends, if you can cook up something which is more efficient than these methods, you will be popular. You will become very popular. Whether that's a goal or not, right? I leave that to you to judge whether that is of interest or not. But these are some of the more famous ones. And you will often see in the literature that people would say that in this specific case, ADA grad works better than ADA. We don't know why, but it does a better job, period. That's a pretty common statement. And that's the kind of experimentation which is nice within the field because there's still many unsettled things. So this typically ADA grad works extremely well if you have a convex function. However, when you deal with neural networks, you don't know whether your function is convex or not. And then ADA grad, you can actually prove that mathematically. It doesn't work that well as ADAM and RMS prop. So if you're dealing with deep learning methods, you would often see that these are the methods of choice. Okay, so sorry for just going through these things, but I wanted to give you the kind of overarching picture of view of what is going to come. There's a question.
In the scheduler?
Yeah. Oh, it's a minus k here, right? Because then it just decays exponentially. So it decreases. No, you actually want to have it to settle down at a specific value. So after some iteration, it reaches a specific value and then it stays at that value. So suppose now that you start with 10 to the minus 4, and then you keep going, it could then decrease to 10 to the minus 4.5, and then it stabilizes there. You will find linear schedulers, and I'm going to list them a little bit later. So you will see the complete list. But these become more ad hoc rules. These are just cheap ways of circumventing the problem that you don't want to evaluate the second derivative. So I've never liked these methods because they, one of the reasons why I normally prefer using these adaptive learning rates is that they keep some information about the gradients. Okay, so the thing I wanted to do now is to show you the type of problem which leads to Newton-Raphson's method. So what we're going to do now is to go back to the cost function and assume now that we are making a Taylor expansion around the optimal value of beta. And when we do that, you're going to see that this is actually going to lead to Newton-Raphson's method, and it shows you what kind of optimization problem we are typically dealing with. So let's take a look at Taylor expansion. Of C of beta around the optimal value, beta hat, minus the value from the previous iteration, beta of k. So suppose now that you have performed k plus 1 iterations, and then you have obtained the optimal value of beta hat. So the hatted values are the optimal parameters, which minimize our cost function or maximize it. So when you then do that, what we end up with is something like this. So let me just bring back my stuff here. So we would have a C of beta. And now what I'm going to do, and I hope that doesn't cause any confusion for you guys, I'm going to let beta be replaced, beta hat, just be replaced with beta. Is that okay? So I don't want to bring too many symbols with me. So I have a C of beta, which is the optimal. So I'm just making a Taylor expansion around the optimal value. Then clearly, this has to be equal to C of beta of at iteration k. We're just Taylor expanding. And then what I have is the gradient G transpose multiplied, because these are now vectors, at beta of k. And I'm going to label this simply as G of transpose at iteration k. And this is then multiplied with beta minus beta of k. And then I have the second derivative. Since these are matrices and vectors, I have to be a little bit careful with the order. So I should have a beta minus beta of k. And this is transpose. And this is multiplied with the Hessian matrix, the second derivative at iteration k, multiplied with beta minus beta of k here. And then I have high order terms, plus O of beta minus beta of k to the power of 3. So what I'm going to do now is to truncate, and simply hoping that the third derivatives and fourth derivatives and so on can be neglected. So I don't want to calculate the third derivative of this quantity. The second derivative is always an ugly beast. So what we are going to do now is simply to approximate it. And I'm also going to introduce a shorthand. So I'm going to define a vector B, which is beta minus beta of k. And then we approximate at second order. The second derivative. So we are hoping that all the higher derivatives multiplied with these vectors, they give a negligible contribution to second derivative. So what we get then is a C of beta, which is now proportional to a C of beta of k, plus this vector b, or actually the gradient, k multiplied with this vector b, plus 1/2 times b transpose multiplied with h, evaluated at beta of k multiplied with b. And then we calculate the derivative of this quantity with respect to this vector b. So taking the derivative with respect to beta is the same as taking the derivative with respect to that vector b. And we want that one to be 0. And when we do that, we know that this term which you have here, this one is just a constant. So when we take the derivative, so what we're going to do now is to take the derivative of dc of beta with respect to the beta, which is the same as taking the derivative with respect to b, and we want that one to be 0. And then what we see then is that we get the following. When we now are using the same rules which we had for calculating the derivatives, you will then see that this is simply going to lead to the following expression. You're going to get beta, which is going to be equal to beta of iteration k minus this matrix H minus. So I just invite you to look at the math here because we're getting at the end of the lecture here. And this is where we're going to start tomorrow. And multiplied with a gradient evaluated at iteration k. And this is nothing but Newton-Raphson's method when I take the derivative with respect to this vector b. So then you're just going to get immediately Newton-Raphson's method. And the only thing we have done now, if you look at this problem here, this problem which you see here is the same as us looking at a function which has a constant plus, and let me just quickly write this down, plus 1/2 times x transpose times a matrix A times a vector x plus a vector g times x. And if I take the derivative of d of f of d of x equal to 0, that is the same as if we setting a times x equal to minus g. And this means that x in that case is simply given by this minus a minus 1 times g here. This is a famous linear algebra problem, which many of you have seen, a standard linear algebra problem, which if the matrix A can be inverted, we can solve that by Gaussian elimination. So what you see now is that what we have done is simply to state that when we look at the Taylor expansion of the cost function around the optimal value, that corresponds to optimize a problem which is quadratic in the unknown quantity x. And now x and a, x is a vector and a is a matrix. And that leads to the standard linear algebra problem with a times x is equal to a vector on the right-hand side, which is known. So this quantity is known, this is unknown, this is the only unknown quantity. So this is a kind of parallel with what we are doing now. And this is how you end up with, when you now take this derivative of this function here, you actually end up with this. And that is Newton-Raphson's method for finding the roots of the first derivative. So tomorrow we are going to look at some further properties of this. And based on that, we are then going to dive into implementations and running Jupyter notebooks and see how we can implement these methods. And then we are going to link these with the first project. I just wanted to say one thing with the first project. You should feel free to use all functionality which exists in NumPy, scikit-learn, and so on. There is no point in writing your own matrix inversion algorithm. That's a waste of time. Okay, guys, we'll take a break and then we see each other tomorrow at 12 and then Wednesday at 10. Thanks for coming, guys.